All right, so chapter 14 is about correlations and regression. So a correlation measures and describes the relationship between two variables by looking at two different variables for each individual. So the characteristics of a relationship depends on the direction. Is it positive or negative or no correlation? And then the form, it should be linear. And the strength of the consistency, which is going to vary from 0 to 1. And all of those characteristics or correlations are independent. So if we take a look at figure 14.2, we see correlational data that shows the relationship between family income and student grades. And we can see that there is a positive correlation because as one score goes up, so does the other score. Here's some examples of positive and negative correlations. So we can see in figure A, we have a positive correlation because as performance in class goes up, it's based on how much time is spent studying. And then a negative correlation occurs when the variables go in opposite directions. As the more a person uses their smartphone, the less they participate in class. Here are some examples of different values for linear correlations. And we can see a negative correlation in A. We can see no correlation in B. In C, we can see a positive correlation. And in D, we can also see no correlation because it's not forming that linear pattern. 14-2 is the Pearson correlation, which measures the degree to the direction of the linear relationship between the two variables. A perfect linear relationship happens every chance that X has a corresponding change in Y. That correlation could be plus or minus 1. And there's a formula to measure that. And the sum of products deviation is similar to the sum of squares. It measures the amount of covariability but that exists between the two variables, and it is indicated by the formula, the SP definitional formula. The definitional formula emphasizes the fact that as the sum of products as the sum of two different scores, that computational formula results in easier calculations. And if we look at figure 14.5, we can see a scatter plot for the data, for example, 14.3. A ratio compares the covariability of X and Y with the numerator and the variability of X and Y, the denominator. The sum here measures the covariability of X and Y. Pearson correlation formula can be expressed as a relationship between z-scores, and z-scores help identify the exact location of each individual score within a distribution. So let's go ahead and do a learning check. A scatter plot shows a set of data points that fit very loosely around a line that slopes down to the right, and which of the following values would be closest to the correlation for these data? Is it A, B, C, or D? And hopefully you chose D as the correct answer. Let's do a couple of true-false questions as well. A set of 10 pairs of X and Y scores has the sum of 20. For this set of scores, the sum of products is negative 20. And if the Y variable decreases when the X variable decreases, their correlation is negative. And true and false. The variability changes in the same direction would be a positive correlation. Correlations have a number of different applications, including prediction, which is using one of the variables to make a prediction about the other variable to say one thing has an impact on the other. Validity measures what you intend to measure. Reliability is the stable, consistent measurements. And the theory of verification is to test a theory by determining the correlation that exists between those two variables. Correlation describes a relationship. It does not show us causation. You may have heard of the term before. Correlation does not equal causation. It just tells us that there's a relationship between two variables. When we establish causation, it requires an experiment in which one variable is manipulated and the other one is controlled. An example 14.4 and figure 14.6 demonstrates the fallacy that can happen if we attribute causation after observing a correlation. So here's figure 14.6. And this is the hypothetical data that shows a relationship between the number of churches and the number of serious crime. It would seem by looking at this that as the number of churches increase, so does the number of serious crime, which would be a incorrect correlation. The correlation coefficient value size would be affected by the range of scores in the data. Severely restricted range may provide a very different correlation than with a broader range of scores. So to be safe, we have to never generalize any correlation beyond the range of data represented in the sample. Figure 14.7 shows us the restricted range in correlation. And then sometimes we have outliers, which is an individual with an X or a Y value that is substantially different from all other data in the sample. It's characterized by a much larger or a smaller score than all the other scores in the sample. In a scatter plot, the point is clearly different from all the other points, and outliers tend to produce a disproportionately large impact on the correlation coefficient. So if we take a look at figure 14.8, we can see the influence of outliers and how they differ drastically from other scores between A, which has no outlier, and B, which has an extreme outlier. A correlation coefficient measures the degree of the relationship between variables on a scale from 0 to 1, or 0 to -1. It's easy to mistakenly interpret this decimal number as the percent or proportion. Correlation is not a proportion, it's a squared correlation, which may be interpreted as the proportion of shared variability. So when we square that correlation, it's called the coefficient of determination. The coefficient of determination measures the proportion of variability in one variable that can be determined from the relationship with the other variable, which is shared variability. For example, a correlation of 80 means that 64% of the variability in the Y scores can be predicted from the relationship from X. So in order to calculate that coefficient of determinism, we're going to use R squared. And figure 14.9 shows us 3 sets of data that show 3 different degrees of linear relationship. The Pearson correlation is usually computed for sample data, but is also used to test hypotheses about the relationship in the population. So a population correlation is represented by the Greek letter rho, or P. And there's some different formulas that can be used for directional or non-directional results. So if you look at figure 14.10, we've got a scatter plot of a population of X and Y values with a near zero correlation. For the hypothesis test, we use a sample correlation R to test the population, with the degrees of freedom being n minus 2. That hypothesis test can be computed using either a T or an F, with only the T shown in this chapter. You'd have to use the t-table to find the critical value of n minus 2 with those degrees of freedom. When we report correlations, we have to report whether it's statistically significant. That gives us concise test results with the value of the correlation, the sample size, the p-value or probability level, and the type of test, whether it's one-tailed or two-tailed. The Pearson correlation has been developed for data having linear relationships, with data consisting of numerical scores from interval or ratio measurement scales, with other correlations that have been developed for data with nonlinear relationships, with data from nominal or ordinal measurement scales. And examples include the Spearman correlation, the phi coefficient, and the point visceral correlation. That Spearman correlation formula is used with data from an ordinal scale, which ranks things. It's used to measure the relationship between X and Y when both variables are measured on ordinal scales. And it may also be used if measurement scales are integral ratio when the relationship is consistently directional but may not be linear. So figure 14.11 shows us the relationship between practice and performance. And figure 14.12 shows us what scatter plots would look like with those scores and ranks for the data in 14.9. When we rank tied scores, a tie score occurs when two or more identical scores are needed for ranks of the Spearman correlation. There's a method for assigning rank, which is when we list scores in order from smallest to largest. We assign a rank to each position in the ordered list. And when two or more scores are tied, we can compute the mean of the ranked position and assign this mean value as the final rank for each score. The ranks for the scores are also simple integers, and those calculations can be simplified when we use D as the difference between the X rank and Y as the rank for each individual to compute the R statistic. The point-Bisset rule correlation measures the relationship between two variables. One variable will have only two values called dichotomous or binomial variables. And for example, a college graduate versus a non-college graduate. One variable has regular numerical scores, and the point-Bisset rule correlation is a special version of the Pearson correlation. The effect size for independent measures t-test in Chapter 10 can be measured by R squared. So that point-Bisset rule R squared has the same value as the R squared computed from the t-statistic. And the t-statistic tests the significance of the mean differences between those two populations that are represented by the samples. That R statistic of the correlation measures the strength of the relationship between the two variables. When we apply the same situation as the independent measures t-test in Chapter 10, we can see that there's dichotomous variables is first converted to numerical variables by assigning a value of 0 to one category and a value of 1 to the other. Then the regular Pearson correlation formula is used to the converted data. The R squared quantifies the effect size and is entirely determined by the size of the correlation. And the T is influenced by the size of the correlation and the size of the sample. For the phi coefficient, both variables x and y are dichotomous. Both variables are converted to scores of 0 and 1, and the regular Pearson formula is used with the converted scores to calculate R. The R squared coefficient of determination will measure the effect size and the proportion of variability in one variable predicted by the other variable. So let's go ahead and do a learning check. Participants were classified as morning people or evening people, then measured on a 50-point conscientiousness scale. Which correlation should be used to measure that relationship? And the correct answer would be C, the point-Bisset rule correlation. And let's try a couple of true-false. The Spearman correlation is used with dichotomous data. And in a non-directional significance test of correlation, the null hypothesis states that the population correlation is 0. Take a few moments to think about those correct answers. And we have false and true. The Spearman correlation uses ordinal or rank data, and the null hypothesis assumes no relationship, with 0 indicating no relationship in that population. The Pearson correlation is going to measure a linear relationship between two variables. Figure 14.3 makes the relationship obvious, and the line through the data makes the relationship easier to see. It shows us the central tendency of the relationship, and it can be used for prediction. The goal is to develop a procedure that defines the straight line that provides the best fit for any set of data. So if you take a look at 14.13, the relationship between math SAT scores and college GPA for engineering students shows a line drawn through the middle of the data points. The higher the SAT scores, the higher then also the GPA. For linear equations, in general, a linear relationship between two variables of x and y can be expressed by the equation y equals bx plus a. Those x and y are variables, and a and b are fixed constants, and the value of b is called the slope, and the slope determines how much the y value changes when x is increased by 1 point. So if we take a look at figure 14.14, the relationship between total cost and number of months in a gym membership, we can also see that relationship. When it comes to regression is a method of finding an equation that describes the best fitting straight line for a set of data, and how to define the best fitting straight line when there are many possible straight lines. The answer is a line that is best fit for an actual data that minimizes prediction errors. Mathematically, we have to define the distance between the line and each data point. Y is the value of y predicted by the regression equation for each value of x. Y minus y is the distance each data point is from the regression line or the error of prediction. And the regression procedure produces a line that minimizes total squared error prediction, and that is the least squared error solution. And we can see that is indicated in figure 14.15. The regression line equation is indicated here. The slope of the line B can be calculated using the formula on the screen, and the value of the constant A is determined by the formula that's also listed on the screen. And we can see in figure 14.16 the x and y data points and the regression line for the value of 8 pairs of scores in example 14.14. When we try to calculate the standard error of estimate, we have a regression equation that makes a prediction, which is the accuracy of the prediction that depends on how well the points on the line correspond to the actual data. We have the precision of the estimate, which is measured by the standard error of estimate. And we can see in figure 14.17 a scatter plot that shows us that, the regression line defined by the equation x plus 4. And here in figure 14.17, we can see another set of data with the regression equation. And when we have the relationship between the standard area of the correlation, as R goes from 0 to 1, we are going to have that standard error decrease to 0. And for analysis of regression, we have the significance of the regression equation, which is a sample correlation, which is expected to be representative of its population correlation. We have the principle of sampling error and the analysis of regression, which uses an F ratio of 2 mean squared values. And it'll show us that the null hypothesis is the slope of the regression line is 0. And we've got some formulas to indicate the significance of the regression equation. And in figure 14.18, we have the partitioning of SS and DF for the analysis of regression. So let's go ahead and do another learning check. A linear regression has B equals 3 and A equals 4. What is the predicted Y if the X equals 7? Give you a few moments to think about this. And the correct answer is B. And true or false, it is possible for the regression equation to place none of the actual data points on the regression line, and if R equals 0.58, the linear regression equation predicts about 1/3 of the variance of the Y scores, And we've got true and true. When the line estimates where a point should be, but there are almost always prediction errors, and we can see that formula. So when it comes to SPSS, here's the output for the example in 14.13. And here's the one for 14.14, 14.16, and 14.18. Here's the scatter plot for the data of determination in 14.1. And I hope all of this information helps you understand a little bit more about correlation and regression.